So we looked yesterday at exponential growth and exponential decay models, and this was a generic model. If the b is greater than 1, that's this value right here, the one right below the x. If b is greater than 1, we get a growth curve, which looks like what? What does it look like? Exponential functions. Yeah. The Superman. I love that I heard that. That was awesome. This is the Superman graph. So it's exponential growth. It has this horizontal asymptote right there. But it grows really, really fast, and I called that the Superman curve, Superman to the moon. Remind me to show you a picture of the Superman ride so you know what I'm referring to after notes. Now, if that b value is between 0 and 1, so if it's like a fraction, like 2/5 or 3/7 or 1/2, okay, then it's not growth anymore. What's it called? Decay. All right. So it's exponential decay. And what does that graph look like? Superman coming in for a landing. Yeah, that's at least that's what I call it. So it looks like this, and again, it's Superman coming in for a landing this time. But again, it has that horizontal asymptote. It gets infinitely close to 0. And I say, I really like these functions because they're really, we use them. Like, this is like math. This is what I wish all math could be. Like, why do we use these things? Well, guess what? This is where we use them. So we have some formulas that we can use to help us figure out how much something is worth when it grows exponentially or decays exponentially. So exponential growth occurs when a quantity exponentially increases over time. And so we have this model that we can use. I'm going to say f of t. F of t is equal to a times the quantity 1 plus r to the t. Instead of x's and y's, we're using time. Time is our x. It's our independent variable. And f is just the result. F is the output, the y value. Now this is growth because we're adding something so it becomes bigger than 1. Okay. What do you suppose I need to do for decay? Subtract, exactly. So it's f of t equals something times the quantity 1 minus r to the t. And again, it's decaying. We're subtracting from 1. That's going to give us something less than 1. And so that's going to give us something that's decaying over time. Now, what do those letters mean? They stand for certain things. So A is the initial amount. We might call that the principal. It's what we start with. It's the initial deposit. It could be lots of different things. R is the growth or decay rate as a decimal. Very important. They're going to say like the interest on that is 2.4%. All right. And so if they give you that 2.4%, we cannot use percentages. So we have to convert it to a decimal, which is what? 0.024. 0.024. Ladies and gentlemen, in case you can't remember that, I would like to point this out, which I point out every day in 8th grade math. Percent is 2 words, okay? When we have something like 24%, per tells you to divide. And cent, how many cents are in a buck? 100, okay? So 24% literally means 24 per cent per 100. So 24 per 100 becomes 0.24 as a decimal. So if you ever forget, just think about what percent means. It means per 100. And if it was 2.4 per cent per 100, that's 0.024. So just so you remember, percent is actually a mathematical phrase, okay? And then T is the length of time that we're dealing with. So all of these letters have definitions, and we just had to figure out what goes where, which is kind of nice. So let's look at number 1. Brooke started her career with an annual salary of $32,000. What do you suppose that's going to be in our formula? The initial amount. That's the A. That's the initial amount. Each year thereafter, her salary increased by 2.5%. What's the 2.5% going to be? 0.025, and that's going to be our R value. Write and use an exponential growth function to find her salary when she retires after 30 years. What's the 30 going to be in place of? Time, T, yes. So they've given us everything. Is this, which one are we going to use? Growth, because she told us our salaries typically grow, although there were many years as a teacher where my salary actually went backwards. So, it's real frustrating. So, F of T equals, our initial amount was 32,000 times the quantity 1 plus 0.025 to the power of 30. So that's all we have to do. We're going to write it down, set it up, and guess what you get to do? Plug it in your calculator. Ladies and gentlemen, I'm going to encourage you, please just write it down. Please write it down for me. It's not hard, and that's all you can do. You can then just plug it directly into your calculator, 32,000 times the quantity, 1 plus 0.025. Use the parentheses, raised to the 30th, and we get 67,122. We're talking about money, so what should we round to? Hundredths place, yeah, 16, so 0.16. Is that a salary you would be happy with? That's about my salary right now after 20 years of teaching, which is an increase over what it was in Arizona after 20 years of teaching. In Arizona, I was making 51,000. Yeah, it was. So, don't become a teacher. Okay. Let's look at number 3. I think this is really interesting. Number 3, Kate drank an energy beverage with 150 milligrams of coffee. What's that 150 milligrams going to be? The initial amount. That's the A value, 150 milligrams of caffeine. That's a lot of caffeine. Do you know how much caffeine is in a standard cup of coffee? 90. Like 50, 40, or 50. They're like 200. Yeah, they're 116. Yeah. No, 114. Yeah, it's. What was the one you tried, and what was it called? I started with an A or something. Oh yes, so the Alani was 200. Yeah. They're so good. They're so bad for you. Okay. I never had any coffee until I had kids. Okay. Yeah. All right, keep going here. All right, each hour, every single hour, the amount of caffeine in her system decreases by about 12%. What's the 12% for us? 0.12 is R. Very good. 0.12 is your R. And then, if it's decreasing, is this exponential growth or exponential decay? Decay, good. Write and use an exponential decay function to find the amount of caffeine in her system after 8 hours. What do we do with the 8? T, that's time. Very good. So we have our function in terms of time is, we're starting with 150 milligrams, and we have 1 minus 0.12, after 8 hours. Predictions. How much do you think is left after 8 hours? Oh, well, that's not a prediction. That's a... All right, 150 times the quantity, 1 minus... Instead of writing 1 minus 0.12, can I just write 0.88?
Yeah.
Yeah? Is that the same thing?
Yeah.
Yeah? Why?
Because 1 minus...
Yeah, inside the parentheses. Very good. Okay, good.
Over 8 hours, caffeine only decreases by 100
Isn't that... This seems crazy, huh?
Or is that real? Or is it...
After caffeine, after an hour,
Kinda right.
I really don't know. I don't know what it is, but
You drink caffeine a lot.
I have no idea. All right. Wow, how do you know how to do that?
About 20 minutes. Wow.
Yeah. This is interesting.
I feel like I had it during lunch.
That was your lunch.
What?
Well, it went from first hour to lunch.
Huh. I'm going to do this one. I don't do half-life this way. We're not going to do this one, so I might have to, I don't do half-life this way. That's a real interesting thing she didn't introduce. We're going to skip that one. So let's, I can describe it for you using this problem. The half-life of mercury-197 is 3 days. Write and use an exponential decay function to find the amount of mercury left from a 50-gram sample after 20 days. So I'm going to draw a picture, and I think if I draw a picture, you'll be able to see what this is really about. So we have the number of days on the bottom. That's our independent variable. And then this is the amount of mercury. What's the chemical for mercury? AG? Oh, okay. AG is gold, isn't it? G. Okay, thank you. Okay. Thank you, guys, all you chemical buffs. Okay. So we are starting with 50 grams. All right. We're starting with 50 grams at 0 days. Now, so what does half-life mean? It means every 3 days, so on day 3, the amount of mercury is now half what it was. So on day 3, what's the amount of mercury we have? 25, okay? And then now on day 6, what's the amount of mercury we have? 12.5. So every 3 days, the amount of mercury is cut in half. So that's exactly what half-life means. And so again, every 3 days, now I was at 12.5, now I'm at 6.25, yeah. And then 9, and then 12 were half, and 15 were half, and then, yeah, 18 were like half. So, and you can see that is what that looks like. So you can sort of just figure it out if you understand what's happening, this is almost as valuable. This question comes up a lot on SAT questions, and again, if you know how to draw a picture of it, could you probably figure out your multiple choice answer, like pretty easily, yeah? All right, so I'm not going to do that one because I do it a different way. All right, so we also have continuous growth and decay. Sometimes the quantity is constantly increasing or decreasing at an exponential rate, and not just every month or every year or every day. Oh my gosh, so is she? Okay. We want to use the formula at the right if things are continuously growing, always multiplying, like the cells in our body are constantly growing and constantly developing. And because this happens in natural things, so this is like, your cells, the biology of things are always continuously reproducing. This is a natural thing. We use E, a base of E. So this is my favorite model, P times E to the RT, PERT. PERT. This is the PERT model. P times E to the RT. P, just like the A in the previous model, is the initial amount. I-N-I-T-I, oh my God, I-N-I-T-I-A-L. All right, it's the initial amount. What is E? What is E? Not quite 3. What is E? Not quite 3. 2.7-ish. Okay, we're going to use our calculator for that. Just like before, R is the rate as a decimal, and what is T? Time. All right, and so a lot of the same thing here. Let's look at number 5. A garbage dumpster started with 4 pounds of garbage. The amount of garbage increased continuously. Because of that word, continuously, I know I'm using the PERT model, P-E to the R-T. By 35% each day. What do I do with that point, 35? 0.35, very good. So R is 0.35. From that point forward, find the amount of garbage in the dumpster after 2 weeks. Ooh, this is interesting. Do I use 2? Why do we use 14? Yeah, this is 35% every single day. So we want to make sure they match. So 2 weeks is actually 14 days. So you do want to read carefully and make sure those sort of match up. What was my initial amount? 4 pounds. So that was my P, the beginning amount of garbage. So, whoops-a-daisy. So 4 times E to the 0.35 times 14 days. Okay, make sure you know where that button is on your calculator. The E to the power is right here in blue next to the 4. So we're going to do 4, and then second E to the 0.35 times 14. How do you do what? So the rate takes care of itself. Yeah. So we get 537 point, I don't know, 2 pounds. Who knows? All right. Number 6, the population of a town is declining at a continuous. Since it's continuous, what model do we use? PERT. The amount is equal to PE to the RT. All right, at a rate of 1.5%, which means we're going to use what for our R? 0.015, yep. If the current population is 16,000 people, where does that 16,000 P? Yep. Find the population in 8 years. So that is our T. So pretty easy. We're starting with 16,000 people. E to the 0.0. Oh, it's declining. You asked a great question. If it's declining, we're going to make that rate negative. Yeah, since it's declining, our rate is going to be negative. I'm so glad you asked that question. Which is just like the other side, that if it's increasing, it's a positive R, and if it's a decay function, it's a negative R. So makes sense there. All right, so negative 0.015 times the 8 years, and what do we get? That's rounded. Oh, okay. So was it 1419.0.7?
Yeah.
Oh, 0.7? But we can't have 0.7 people, yeah. I think that this is fine. Did your calculator say something different?
I got 1400.
Yeah, 0.015 times 8. Oops. I should have just done it in my calculator, but All right, did you figure that out, Thomas? Okay, great. Okay, now my favorite model. My favorite model is the logistic growth function. This is actually what really happens with population growth. And so you can see here, sometimes the quantity exponentially increases, but then levels out, approaching this horizontal asymptote. So this is a logistics curve. It sort of goes slow, then it goes really, really fast, and then it slows down because it levels out. Now, why do things level out? So reaching max potential, yes, I'm going to say your environment restricts you, right? So imagine a pond of fish. Early on, when you have just a couple of fish, there's this whole wealth of pond to eat and grow, whatever. As your population of fish increases, what happens to the resources available in that small pond? It decreases, right? So you can't find food as well. You can't move around as much. You don't have as much to be able to continually grow. So now your population starts to get limited. So here on Earth, we're going to run out of natural resources, right? And eventually we just won't be able to sustain ourselves. There won't be enough food. It's a really bad thing for a math teacher to think about. So we are pretty much doomed. So we will level out. And so most populations grow like this. The United States, our population is leveled off because we don't have a lot of kids now, right? Like you don't typically see a family with a dozen kids anymore. A couple generations ago, that might have happened, but now it's like if we're good with one or two, we're good, right? So we don't have that growth. What's happening in China?
They're limited. Yeah, they can only have 2 kids.
Well, now they can have 2, but they had the one child, right, for the longest time. And what happened now? They don't have enough young people, like my age people, to support all of the older folks. And so they have this huge, like, we don't have enough workers to work anymore. So they self-limited, and now it's kind of causing a problem. All right, so this is called a logistic growth model, and I think they're really, really cool. So here we have disease begins to spread in a town with 20,000 people. And again, this is a great application of a logistics model. Why would a virus spreading have a logistics growth model?
Because
There's so many populations.
Well, it does grow for a really long time. That virus spreads, but then what happens once it spreads to... Everyone's been infected already, so it's much harder to get someone infected, right? So that's what happens, it slows down. You can see that 20,000 is on top, that's the initial amount. And after T days, the number of people who have been infected by the disease is modeled by this function below. Using a function, find the number of people affected after 10 days. What do they want us to do with the 10 days? Plug it in for T right there. So we have 20,000 people, oh, that's too many zeros, over 1 plus 1150 e to the negative 0.95 times 10 days. So we are just plugging in the 10. Now, what's going to be problematic with this? So it's hard to plug into your calculator. That's what's problematic. How do you guys want to do this? So we could do that. You could do the denominator first and then do 20,000 divided by that answer. For those of you that had Nacho, you do the fraction. Alpha F1, and you could do the little fraction thing. All right. So do you guys know that? I don't know that you guys all do. Okay. All right. So alpha F1 is a numerator denominator fraction. So 20,000 over 1 plus 1150 e to the negative 0.95 times 10 years. So you get that all plugged in? And it's, 18,415 people, roughly. I'm going to put a little approximation symbol there because that's not exact. All right, so after 10 days, wow, that was a quick spreading virus. All right, do you guys have any questions for, oh, let's do one, no, let's not. I'm sure you can figure it out. All right, super.
Is it a worksheet?
It is a worksheet.